Hello everyone. Welcome to ArcPy, Solving Large Transportation Analysis Problems. My name is Melinda Morang, and I'm here with my colleague Dilesh Mandloy, and we're very excited to be talking to you about this today. Today we're going to start with a brief introductory and background section, then we'll talk about some techniques for solving large problems. Then we'll walk through a Python script that will talk about solving large problems using a local network dataset using the techniques we discussed. Then we'll talk about working with services, and then finally we'll take another look at that Python script to show how you can solve the analysis with a service. We realize it can be quite difficult to follow along with code in a presentation like this, so all of the code as well as these slides are available for download at this address. Go ahead and take a moment to make a note of it. We'll show it again at the end in case you miss it. Let's start off with a brief introduction. The ArcGIS Network Analyst extension is the part of the software that's for solving transportation analysis problems. It has tools for assessing the coverage of different facilities, for optimizing things like site location and fleets of vehicles, and for point-to-point routing, such as how do I get from point A to point B? What's the closest facility? And for solving origin-destination cost matrices. In today's presentation, we're going to be talking about the origin-destination, or OD, cost matrix. Although we'll be focusing on this tool, a lot of the techniques we'll be discussing apply to the other network analyst tools as well. OD cost matrix is used for finding travel time or distance between sets of origins and sets of destinations. This tool has the ability to use a time or distance limit, which is important for large problems. You can also limit the number of destinations you want to find. So instead of saying, what's the travel time from every origin to every destination, you can say, what's the travel time from every origin to the 5 closest destinations, for example. So what is a large problem? A large problem is one that can't be solved in one calculation, maybe because it would involve an unreasonably large calculation time, or maybe you hit some memory limits on your machine. If you're using a service, maybe you run into some limits of what the service is capable of providing. Usually large problems involve a large number of inputs, but they may also be large because the output is large. For example, with an OD cost matrix, that the result comes back as a table that includes the number of origins times the number of destinations. If you have 1,000 origins and 1,000 destinations, your output has 1,000,000 records in it. So the output can sometimes be the large part. Some examples of a large problem include calculating the drive time for all patients to all medical clinics within 100 miles, or calculating the network distance from every parcel to every other parcel in a city. Today's goal is to create a script that we can use to solve a large OD cost matrix problem using any number of origins and destinations, local data or a service, with or without a time or distance limit, and outputting the results to a single feature class. Now, I've mentioned local solve versus services solves a couple of times. What am I talking about? A local solve means that I'm solving the network analysis problem on my own computer using my own network dataset stored on my own disk. I'm using the computing resources of my own machine to solve the problem. When I'm referring to a service, what I mean is solving the network analysis problem using some kind of GIS web service. The data is sent to the service, and the computing resources of the server are used to calculate the result, and the result is sent back to me. Both of these are a valid way to solve the problem, and it really depends on your situation. We'll go into this a little bit more later. Which product should I be using, ArcGIS Pro or ArcMap? We recommend using ArcGIS Pro for solving large problems. Pro is a 64-bit application, so it can use the full memory resources of your own machine. You can solve problems in Pro that might have caused memory issues in ArcMap. It also has a much more seamless integration with services. ArcGIS Pro also has the ArcPy.nax or NAX module, which provides a very nice, clean, and fast set of classes and methods for doing network analysis that's easier and less clunky than using all the network analysis layers and geoprocessing tools that you need to use in ArcMap. ArcMap, on the other hand, is a 32-bit application, so it tends to run out of memory. It can't use the full memory resources of your machine. If you want 64-bit capabilities, you would have to install the 64-bit background geoprocessing extension or use ArcGIS Server. It's much less simple to use with services, and it doesn't have the new ArcPy.nax module. For the rest of this presentation, we'll be showing code designed to work with ArcGIS Pro. As I just mentioned, ArcGIS Pro has a Python module for performing network analysis, ArcPy.nax or NAX. This module features easy-to-use classes and methods for performing network analysis using either local data or a service. This is a summary of the workflow that you'll want to use for performing a network analysis, such as calculating an OD cost matrix. First, you initialize the analysis object, and that object is based on a specific network data source. Then you set the properties that you want for the analysis. Then you load the inputs, solve the analysis, and then finally work with the results. Each type of network analysis or solver has its own Python class. When you instantiate the solver object, you need to set the network data source. This can be either a network dataset or a URL to a service, such as ArcGIS Online, or a service running in your own portal. Once you instantiate the solver object class, you can set the various analysis properties. You can see the properties for the OD cost matrix object here in the slide, including the travel mode that you want to use for the analysis and the default destination count and default impedance cutoff settings, which we'll talk about a little bit more later. The class has methods for loading data as well as solving, and some other helper methods. When you solve the analysis using the solve method, it creates an instance of a result object for that particular solver. You can access the analysis results from that result object. The scripts that we're going to show today will make use of these solver objects, and you'll get to see these in use later. All right, now let's transition to talking about some techniques for solving large problems. Some techniques include reduce the problem size, eliminate irrelevant data, chunk the data, spatially sort the data, solve in parallel, pre-calculate your network location fields, and use a network dataset layer. I'm going to go through each one of these in more detail. The first thing to do is to reduce your problem size. You might find out after you've done this that you don't actually have a large problem after all. One thing you can do to reduce the problem size is to find only the k nearest destinations. Do you really need to find the travel time between all origins and all destinations, or can you just find the 10 closest destinations? For example, do you need to calculate the driving time from a patient to all doctor's offices, or can you just return the 10 closest options? The OD cost matrix tool has the ability to limit the number of destinations to find. You can use the default destination count property on the OD cost matrix solver object to do this. You can also use a time or distance cutoff limit so that you can only find destinations that fall within this limit. Do you care about results that are more than 100 miles away? For example, if your patient is located in California, you probably don't need to give them doctor's offices in Maine as options. You can use the default impedance cutoff property of the OD cost matrix solver object to set a limit like this. Another thing to do is to eliminate irrelevant data. This is related to reducing the overall problem size, and this applies primarily to the case where you're using a time or a distance limit. If you only care about finding destinations within 100 miles network distance of each origin, you can exclude from the analysis any destinations that are more than 100 miles straight line distance away, because you know that those destinations will never be included in the solution. This drastically reduces the number of inputs that you have to send to the OD cost matrix analysis in the first place. Now, you don't know the driving distance from the origins to the destinations prior to running the OD cost matrix. However, the network distance from an origin to a destination will always be greater than or equal to the straight line distance. Consequently, you can do a quick straight line distance calculation first to eliminate all the destinations that are outside of your cutoff, maybe using some small additional buffer just to be on the safe side. You can do this using the Select Layer by Location tool, which selects only the destinations within the specified straight line distance of any origin. One thing to watch out for when using this tool is the case where no destinations are found within the cutoff distance. The Select Layer by Location tool, rather than returning an empty set, just returns the entire data set. So you have to explicitly handle this case in your code. Once you've reduced the problem size as far as you can, you'll probably want to chunk your data and then solve each chunk iteratively, perhaps in parallel. So you'll want to create chunks of origins and chunks of destinations. For each chunk of origins, you'll calculate the travel time or distance to the destinations in each chunk of destinations. Once you've finished with the first chunk of origins, then you move on to the next chunk of origins and run it against each chunk of destinations. The chunk size really depends on the memory resources of the machine you're using to solve the problem, or the limits of the service that you're using. Some services, like ArcGIS Online, have limits to the number of inputs that you can pass in. Don't forget to consider the number of origins times the number of destinations, or more generally, consider the size of the output that will be returned by the chunks. Something you can do to improve your chunking is to spatially sort your data. This allows you to make smarter chunks that will overall reduce the number of iterations you need. You can use the Sort geoprocessing tool to spatially sort by selecting the shape field as the sort field and using the piano curve method. This method makes the points all nice and clustered as it goes through the dataset. One thing to note is that this spatial sort option requires the advanced license. The last couple things I explained were a little bit confusing, so I'm going to walk you through an example to make it clearer. Let's say I want to solve a problem where I have 26 million origins, that's the purple dots, and 200,000 destinations, that's the orange squares. I want to calculate the travel time from each origin to each destination if the destination is within 100 miles of the origin. Let's say my chunk size is 1,000, and I just randomly select 1,000 points from my origins. They're scattered all over the country, as you can see here. Then let's try to reduce the number of destinations relevant to this chunk of origins by eliminating any that are over 100 miles straight line distance from any origin in this chunk. I'll use the Select Layer by Location tool. The selected destinations are all the ones that are still relevant for this chunk of origins. They're within 100 miles of at least one of my origins in this chunk. Because my origins are scattered all over the country, I end up selecting about 98% of the destinations that were there in the first place, so I haven't really successfully reduced the number of destinations that I have to handle for this chunk of origins. So if I'm using a chunk size of 1,000, for this chunk of 1,000 origins, I'm going to have to run through about 215 chunks of 1,000 destinations, and it's going to take a while. Let's say that I first spatially sort my data. Now, let's say I just select a chunk of 1,000 origins. All of them are right there in the Palm Springs area, that tiny little purple dot. Then, if I select destinations that are within 100 miles of these sorted origins, there's fewer than 6,000, which is only about 3% of the destinations total, as opposed to the 98% that I got when I didn't sort my origins. Now, for this chunk of origins, I'll only need 6 chunks of destinations, and I can be confident that all of the other destinations are completely irrelevant for this chunk of origins. Thus, I've substantially reduced the number of chunks that I need to process overall. Assuming I've done my chunking, I now need to solve my OD cost matrix in parallel. So instead of doing each chunk one at a time, I can solve several chunks at once, and that will ultimately return my results faster. Python makes this easy with the concurrent.futures module. Concurrent futures gives you 2 options for doing things in parallel, multiprocessing and multithreading. Multithreading is not too great for CPU-intensive problems in Python, and it doesn't work very well with ArcPy, so we don't recommend using that. We recommend instead using multiprocessing. This allows you to spin up multiple processes and run your solves against multiple cores. It works nicely with ArcPy, and it's really easy to run from standalone Python. A couple of things to watch out for. If you're trying to write a script tool that runs within ArcGIS Pro in the UI, it won't work with multiprocessing directly. You'll have to spin up your process as a subprocess using the subprocess module. Then you can spin up all of your additional subprocesses in parallel. You also can't write to the same file geodatabase using multiple processes at the same time, so you'll have to be careful about how you're storing your output. Dilesh will demonstrate how to handle these challenges in his sample script later. If you're using origins and destinations more than once, like in chunks that get used more than once, you can speed up the calculation by pre-calculating your network location fields. What are network location fields? These describe where each point snaps to the network. A point is usually just somewhere floating in space, and the network location fields describe the closest point on the network dataset that's used as the actual beginning and end point of the network analysis. Each time you do a network analysis, the solver has to determine what these network location fields are. If you're going to be using the same origin or destination multiple times, it doesn't make sense to waste time recalculating the network location fields each time you solve a chunk, since the network location fields for a specific point aren't going to change. It's more efficient to pre-calculate the network location fields and just use those. You can do this with the Calculate Locations geoprocessing tool. The fields get stored in your tables, and then when you load the origins and destinations, you can use field mappings to map the existing location fields, and the solver will just use those. Note that if you modify your network dataset or decide to use a different network dataset or travel mode, you need to recalculate your network location fields, since those are specific to the network dataset and the travel mode settings. The Calculate Locations tool doesn't work with services. You can only calculate network location fields with a local network dataset. Technically, you could pre-calculate network locations if you're going to solve using an ArcGIS Enterprise service by running the Calculate Locations tool with the same network dataset that the service is published with. But that's beyond the scope of this presentation, and our sample script tool doesn't do that. Finally, assuming you followed all of the other suggestions so far, you can get a small additional performance improvement by using a network dataset layer instead of a catalog path to a network dataset in your script. If you use a catalog path, the script has to open the network dataset behind the scenes every time you reference the catalog path, and it can be especially slow if you're using licensed data or data on a UNC path. If you instead use the Make Network Dataset Layer tool to open the network dataset once as a layer and then pass that layer by referring to the layer name in other tools that use the network dataset, then that can give you a bit of a performance improvement. I'm going to hand it over to Dilesh in just a moment to show you some code, but first let me give you an outline of what that code is going to show. Recall that the goal of today is to solve an OD cost matrix of any size using local data or a service and write it out to a single feature class. The script has a couple of main components. The pre-processing component will spatially sort the data and calculate the network locations. Then there's a section for solving, and that will chunk the data and solve it in parallel. And finally, there's a post-processing section that merges all the results together. Also, as a reminder, the network analysis workflow using ArcPy.NAX has these 5 steps. Initialize the analysis object based on the specific network data source, set the properties for the analysis, load the inputs, solve the analysis, and then finally work with the results. Okay, Dilesh, let's look at some code.
Thank you, Melinda. So in her slides, Melinda showed you the concepts on solving large network analysis problems. What I'm going to show you next is a code sample that we developed, which will put these concepts into practice. Now, at the beginning of her presentation, Melinda showed a URL where you can find the conference slides as well as this code sample. That URL takes you to the GitHub site. If you're not familiar with GitHub, I would like to show you where you can download this code sample and then how you use the code sample. So you go to the GitHub site, under releases, click on the latest release, and then download this sample as a zip file. Once you have that zip file on your local machine, you unzip it and then you add the folder where you unzip that file to your ArcGIS Pro project. So here I have ArcGIS Pro with some sample points that I would use as input. I have unzipped my zip file and now I'm viewing the contents of that folder in the ArcGIS Pro project. So the zip file will give you a toolbox which contains a geoprocessing tool. If we look at this geoprocessing tool, it takes certain inputs such as the origins, which are the points from where you would start your OD analysis, the destinations, the points where you would end the analysis, the network data source, which can be either a local network data set or it can be a ArcGIS Enterprise service or an ArcGIS Online service, the travel mode that you want to use for the analysis, the output folder where the tool will write all of its output. Now, if your OD analysis is using any cutoffs, you'll specify the cutoff, or if you're only finding certain number of destinations from each origins, you would specify it here. The maximum OD matrix size essentially defines the size, the maximum size of a problem that you can solve. And then the parallel processing factor defines how many number of parallel chunks you can solve for a given problem. So these are the inputs, and when we click the run button, this geoprocessing tool will run the Python code associated with it, and that will solve your analysis. So now let's look at the Python code which runs behind this geoprocessing tool. Now I'm using Visual Studio Code as my IDE, and I'll show you some parts of the sample code in this IDE. This sample tool is made up of about 675 lines. So I'm not going to show you every single line of this code sample. My idea is to show you important parts of this sample so that when you read this on your own or try to adapt it, you will have an idea on how to get started and how to look at the different portions. The geoprocessing tool that I just show you references this ODCM_GP tool file. Now this file essentially calls a command line tool called odcost matrix, odcm.py stored in this file, and that's what we are going to look at. Now this odcm.py has four main parts. There is a class called odcost matrix, and then there are three functions. The CLI function essentially takes all the command line inputs and then calls the main function. So we are not going to look into that. Now let's look at the main function. So this is where all the execution starts, and we'll go through it from top to bottom to understand how this sample is working. So the first step in this main function is to create the output workspace. So this is the file geo database that will contain our eventual results. So we create that output file geo database in these lines. Next, we do some pre-processing on our inputs in this pre-process inputs function. So let's look at what this function is doing. Now, as Melinda was talking about in her slides, the pre-processing part involves essentially spatially sorting your input features and calculating the network locations for those features. Now, the spatial sort function creates a new feature class. So that's why we want to preserve our original copy. So we make a copy of the input features, and then we add a unique ID field on our copy so that we preserve the object IDs from our original inputs that we can later use to join additional fields. So that's what is done in these two sections. We make a copy and then we add a unique ID field, and then we transfer the object IDs onto that field. Next, we use the sort geoprocessing tool to spatially sort our inputs. Now the sort geoprocessing tool is only available with an advanced license. So we do some license checking, and if the license is not available, we essentially skip the sorting. Next, we calculate the network location fields by running the calculate locations function. Now this function will take your inputs and the network dataset and figure out where those points are located on the network, and then would write those information back on your features. So this is what we do for the pre-processing. So let's get back to where we started. So we pre-process the origins and we pre-process the destinations in these two steps. And then we keep track of those pre-processed origins and destinations. Next, we get a count of origins and the count of destinations so that we know how many origins and destinations we are working with. Next, we determine if we are working with a local solve or whether we are working with a service solve. And if we are working with a service solve, what different types of service solves we are working on. Now, we have not looked at the slides on the service solve, so we'll get back to this portion of code in a later demonstration. For now, let's look at this else block, because this is what would get executed if we are not doing a service solve. So here we first get the OID ranges. So let's look at what this function is doing. So get OID ranges returns you an iterable of the OID ranges for the origins and destinations. So it takes the origins count and the destinations count and the max OD size. Now remember, when I was showing you the geoprocessing tool parameters, there was a parameter there called max OD size or maximum OD size. So this parameter is essentially used here to figure out what is the size of the chunks that you should divide your big problem into. So for example, if you have 200 origins and 100 destinations, and let's say your max OD size is 10,000, which means we have to come up with chunks such that any chunk does not produce more than 10,000 lines. So in this case, this function will break this up into these OID ranges such that you process the first 100 origins and the first 100 destinations, and then you take the next 100 origins and process them with the 100 destinations that we have, so that anytime we are not processing more than 10,000 in this example. So that's what we do here, and then we return those OD ranges back. So let's get back to where we started from. So now we have got our OID ranges. Now next we start processing each of our chunks. As Melinda was describing, we use the process pool executor class from the futures module, and this class takes the maximum workers, which is essentially the number of parallel processes you want to run. Now again, this input is coming from our geoprocessing tool where we had the parallel processing factor, which by default was specified as 3. So in this case, this class would essentially run 3 parallel or 3 processes. And what we need to do on each of these processes, that's what we specify here in the by calling the map method. So this map method takes the function that you want to run on each of the process and then what inputs should be used by that function. So we are saying, okay, start 3 processes and on each of the process run this solve OD cost matrix function and pass this inputs iterable and the ranges which we essentially calculated previously to this function which is running on each process. So let's look at what this solve OD cost matrix function is doing. So the solve OD cost matrix function initializes the OD cost matrix class and then calls the solve method on it. So first let's look at what is done as part of the initializing that class. So here we are in the constructor of that OD cost matrix class. We essentially store the variables that we need here and some other additional attributes. And now we create a unique workspace that will contain the inputs and outputs for our OD cost matrix computation. Remember, each process is writing its own file geodatabase that will contain the outputs from that process. So that's why it's important to create a file geodatabase with its own unique ID so that you're not writing to the same geodatabase from the multiple processes, because a file geodatabase does not support that. Once we have done that, we make the network dataset layer in this function so that each process, when it is solving a chunk, can make use of the layer and does not have to read the network data source from its catalog path. Next, we get the object ID fields and use them to do the field mappings. So let's get back, and once we initialize the function, we then call the solve method on the class. Now this solve method takes certain inputs and then would do your analysis. So let's look at this solve method one by one. So first, in the solve method, we figure out if we are doing a service solve or we are doing a local solve. So we have not looked at the service solves. So for this demonstration, I'm just going to look at the local solve case. So we should be at this code block, and here we also need to check out the network analyst extension license because all of the analysis is happening locally on our machine. Next, we create the OD cost origin destination cost matrix class. We initialize it. Now here we are following that 5-step workflow which Melinda described in her slides. We initialize the analysis class, in this case origin destination cost matrix. Then we would load all the inputs in it, solve the analysis, and then work with the results. So we initialize the origin destination cost matrix class, and then we set the analysis properties based on what is required for our workflow. So we set the cutoff and we set the target destination count that we have received from our tool dialog. Then we figure out which origins and destinations we want to process. So that's done in this select inputs function. So let's look at that function. So we have all of our origins and all of our destinations, and for each chunk we need to make sure we select only the origins that we want to process. So we do this by constructing a where clause which is based on the origins criteria and the destinations criteria. This criteria is nothing but the OID ranges that we had calculated earlier. So here we figure out, let's say if we want to process the first 100 origins, we would say the where clause is the origins OID is greater than or equal to 0 and less than or equal to 100. And then we make a feature layer so that we only select those origins. Similarly, we create a destinations layer, and then we use the destinations criteria and create the destinations layer. Now, if a cutoff is specified, as we had seen in the slides, we can essentially further filter down the destinations that we want to process. So if a cutoff is specified, and if the cutoff is minutes based, we use a simple formula to convert those minutes to miles. And then we use the select layer by location function to essentially only select those destinations that are within our specified cutoff. Now, one point to keep in mind here is If there are no destinations within our cutoff, then select layer by location would essentially return all of the destinations, which is not what we want. So we specifically check for that condition here. And if we don't get any selection set, we don't get any destinations in our criteria, then we essentially write out a message and return. Now this is important. Or if you don't check for this condition, then you would end up processing all the destinations, which will defeat the purpose of the chunking that we are trying to achieve here. So once we have selected our inputs, we need to do some field mappings. So field mappings essentially takes the attributes from your inputs and pass that to the analysis. So here we say pass the candidate fields, and then for the name field, we say the unique ID field that we had on our origins, we load that as name, and the same thing we do for destinations. We also, by specifying this Boolean true, we also say if the inputs have locations field, pass them also to the analysis. So we create this field mappings object, and then we use the load method on our solver object to load the inputs, and to this load method we pass the field mappings. So far we have created the OD cost matrix class, set some analysis properties on it, and then loaded our origins and destinations into it. The next step is to solve the analysis. So we just call the solve method on our solver object, and then we figure out if the solve did not succeed, we return with a message, and if it succeeded, then we save out first the analysis results as a layer file, so that in case you want to visualize those results in ArcGIS Pro, you can do that. And then we start post-processing the outputs. So we take the OD lines and export them to feature classes. So in this case, we are constructing the paths, and then we export them to the feature classes. And after the export, we use the unique ID fields and transfer some of the attributes, essentially the origin OID field and the destination OID fields, so that we can then later on take our output lines and then join additional attributes from our origins and destinations if we need to. So that's how the solve OD cost matrix function was working with our parallel processes. So once we have all the results from all of our parallel processes, we essentially take them and then merge the individual OD matrix feature classes. So we created multiple chunks and then solved each of the chunk on a parallel process, collected all the results from those chunks, and then merged them into a single feature class. After that, we clean up all the intermediate outputs that we have created as part of the process.
Melinda talked about local solves, and I showed you in the code how you can do local solves. Now let's see how you can solve the same problem if you're working with services. As we said, you have two options, local solve and service solve. Service solves actually have two sub options, ArcGIS Online or your own ArcGIS Enterprise service running on your own servers. Which do you pick? If you don't have any street data, the only option is ArcGIS Online because the street data is provided there by Esri. If you don't have a Network Analyst extension license for ArcGIS Pro or ArcGIS Enterprise, then ArcGIS Online is your only option. You don't need the Network Analyst extension, just the service credits. However, the ArcGIS Online service imposes limits on the size of the problem you can solve. 1,000 origins and 1,000 destinations in a single request is the limit enforced by ArcGIS Online services. If you have a very large problem, you might need to use a large number of chunks. Also, the number of credits required to solve your problem might be unreasonably large. So these are some things that you should consider if you want to pick the ArcGIS Online service option. You can solve locally on your own machine if you have your own street data and the Network Analyst license. So you should do a local solve if you just have one machine with ArcGIS Pro running on it. However, if you have ArcGIS Enterprise, you can speed the problem up by running the process on a bank of servers. Each server can process chunks for you in parallel. You can have as many servers as you want, and you don't have the same analysis input limits that you do with ArcGIS Online. If you're working with ArcGIS Online, you have to worry about two things: credits and limits. The ArcGIS Online services charge credits for each solve. For OD cost matrix, it costs 0.0005 credits per input origin destination pair. So if you send in 1000 origins and 1000 destinations, and even if you want to find the one closest destination for each origin, ArcGIS Online still charges you for 1 million pairs, not 1000. For this reason, it's especially important to reduce your problem size using the techniques we described earlier. You don't want to send irrelevant destinations to the service because you will be charged for them. Make sure to estimate the cost of your analysis in advance to determine how many credits you will need and determine if it's more cost effective to do this or to invest in your own street data. The other thing you need to consider with services is whether the service imposes some limits on the number of inputs. For example, the ArcGIS Online services limit the OD cost matrix analysis to 1000 origins and 1000 destinations. These limits determine the maximum chunk size you can use when breaking up your large problems. Now you can use the get web tool info function to retrieve tool limits from a service dynamically in your script. That way you don't have to hardcode any values that might change. We will show this technique in our sample script in just a minute. If you're using ArcGIS Enterprise, you need to publish the OD cost matrix service. You can do that using the Publish Routing Services utility which ships with ArcGIS Enterprise. You can learn more at the link in the slides. Now this tool takes in a network dataset and publishes the service in your ArcGIS Enterprise. The tool publishes the services with default parameters, but if you're using the service to solve large problems, there are certain settings you should configure on your service. Now I'll briefly describe these settings that you should consider changing. The first one is the number of service instances. Now this setting depends on the number of physical cores you have on your server and how many servers you have. So if your servers have 4 physical cores, you should change the number to 4. This makes sure you have 4 service instances running on the server simultaneously, and each instance can solve a chunk. The next setting you should consider is the execution time for a request. By default, the setting is set to 60 minutes. So if a request takes longer than that, it will time out and return an error. Now, if you're solving a large OD, the request can take longer than that. So I recommend you set this to a higher number, like 4 hours. The next setting you should consider is the number of features returned from the service. Now consider the number of output records likely to be produced by each chunk of your OD and then set this number accordingly. So if your each chunk is say producing 10 million records, then you should set this number to 10 million. So now let's look at some code which would demonstrate how you can solve this same large OD problem that we had initially looked at to solve using a local solve. Now we would see how we would do that same processing using a service solve.
So in our last set of slides, we looked at what a service solve is and what are some of the things you should keep in mind. So now let's see how we can solve this same large OD problem that we previously solved using a local solve. But this time we will see what changes we need to do so that we can solve this problem against a service, or what we are calling it as a service solve. So there are not that many changes from what we had already looked at when we were looking at the local solves. Now I am still in my main function in the odcm.py file, and here after I have done my pre-processing, I now figure out if I am working with a service. So I take my network data source that I get from my geoprocessing tool, and I then figure out, is this a local network data set, in which case I will end up doing a local solve, or if this network data source points to a service, I will end up doing a service solve. So that's what we are figuring out here. Now In our slides, we also looked at when you're doing a service solve, it can either be against ArcGIS Online or it can be against an ArcGIS Enterprise service. So we figure that out here. Now, if it's against an ArcGIS Online service, there are some additional constraints that we need to account for. Essentially, first we need to get the limits for the ArcGIS Online service. So here we call the get web tool info function and essentially return the limits for our ArcGIS Online service that we will be working with. From those limits, we figure out the maximum origins and maximum destinations that the service supports and that we should take into account. Next, we figure out the OID ranges, passing the origin count, the destination counts, and the maximum origins and the maximum destinations. So if you remember from the local solve, we had a very similar function, but that took the maximum origin destination lines as a criteria. In this case, we are creating our OID ranges based on the maximum origins and the maximum destinations. So let's say, look at this example here. So let's say we have 1500 origins and 1200 destinations, and we know the ArcGIS Online service only supports 1000 origins and 1000 destinations. So if we pass all the 1500 origins and the 1200 destinations in a single solve, the ArcGIS Online service will return a failure and we will not be able to do our analysis. So we need to break this OIDs in such a way that we are only accounting for a maximum 1000 origins and 1000 destinations. So what this function would do is take your first 1000 origins and then process them with the first 1000 destinations. Then take your first 1000 origins again and then process them with the remaining 200 destinations. Similarly, then we move to the next 500 origins and process them with the destinations and so on. So we have broken our problem into multiple chunks and then we can solve each of these chunks in parallel. Then we return this OID ranges back. So once we have our OID ranges, we again follow the same pattern that we have looked before. So we use the process pool executor and launch a certain number of parallel processes. On each of those parallel processes, we run the solve OD cost matrix function and pass our ranges that we had just created. And as we had looked before, the solve OD cost matrix function initializes the OD cost matrix class and then calls solve on it. So let's look at how this solve works when working with a service instead of a local solve. So we first determine if we are working with a local solve or with a service solve. If we are working with a service solve, we set the network data source to be the URL to the URL of the service. And in this block, we don't have to check out a network analyst extension license because the processing is being done on the service. So the service is essentially the component that needs to have the network analyst extension license, not your local machine. Then after that, we initialize the origin destination cost matrix solver object, passing our network data source, which in this case will be a service URL. And after that, we essentially don't have to make any single change to our code. So the solve exactly behaves like it was working for the local case. So we again do the 5 steps in this. We had initialized the object. We set the properties of the analysis, including the target count and any cutoffs that we have. We again select the inputs based on the OID ranges that we had created. We do the field mapping so that we can pass the OID fields as the name field. Then we load the origins and the destinations. We solve the analysis and then we export the results from the analysis to the file geodatabase feature class and also transfer the OID fields from our analysis to our outputs. And then once we have collected the results from all of the chunks, we essentially merge them into a single feature class and do the cleanup. So the point I want to emphasize here is the code for working against a local solve versus a service solve is very similar. The only difference is you have to initialize the solver object with either a path to a network dataset when you're working with the local solve or with the URL to the service when you're working with the service. And when you're working with the ArcGIS Online service, you have to account for certain additional constraints like the service limits imposed by the ArcGIS Online service. So now I will hand it over back to Melinda so she can wrap up the presentation.
Thanks, Dilesh. To give a recap of the techniques we talked about today for solving large problems, first, reduce the problem size, then eliminate irrelevant data, chunk the data, spatially sort the data, solve in parallel, pre-calculate network location fields, and use a network dataset layer. Again, here's a link to where you can download the code and the slides that we've shown today. Thank you very much for attending our presentation. And please provide your feedback for this session by clicking on the session survey link directly below the video.